If you go early, it'll stop. Let's see. Pardon me while I'm just make sure the thing is running. Okay, it says it's fair. Is it? Okay. Pardon me while I'm just make sure the thing is all right. Good deal. So we're off to the races. So. Give it a minute. You know what? I probably do need to back away a little bit. That way, you know, I can use the mouse right here. All right. So, how's the focus? Is it okay? The focus is okay? Okay. Going for right there. All right, so we sort of, okay. Wait a minute. Let me make sure. I'm trying to remember. We already did that. We already did the position vector. Okay, so really, I think we're into the dot product and cross product here in a second. I mean, you know, I'll come back and work one out of here, but let me head. Okay, so. All right, so I'll do the dot product for a second. Actually, I kind of think it looks a little strange up on the screen, but oh, okay. So I kind of think this should have been done in the text earlier, but I didn't write the text, and so, and I'll show you why I think it should have been done earlier when we go through it. First of all, when he has things written in this dark, that to me, I have to put an arrow over it. Most books indicate a vector with an arrow on top. He, in fact, wants to make them dark. And then actually, the A and the B here, which are not bold, that's actually the length of the vector. So he's not really following the, I don't want to say correct and incorrect mathematical procedures. So I like to write it the other way. So in other words, this equation actually could be written as vector A dotted with some vector B is equal to magnitude of A and the magnitude of B times the cosine of the angle between them. Now, when you look at some textbooks, they'll do this and put a subscript AB, kind of indicating that it's the angle between the vector A and B. I won't even do that here, but this is kind of the typical math representation. So I'm going to quickly cover what he's got, and then I'm going to go through and look at the implications compared to what we already did. I think I double-clicked it, so that means zoom in, I guess. So he has this law's communicative law, the multiplying times a scalar, and then distributed. And for that matter, the dot product pretty much is okay with the cross product, not, but we'll get to that when we get to it. If you look at him, and he's starting to look at something interesting here, and that is you can represent your vectors A or B and B as the components times the base vectors, And you notice in the text here, he bold-faced the I, the J, and the K. But this is not bold-faced. So these are scalar values. These are the scalar ones, and these are the vector ones. The other ones are the vector ones here. So you go through and do that, then what he does is you look at the multiplication. Well, what you're supposed to do, okay, and I'll try to see if I can do this. So if you look real close at what he does, the first row, I'll circle them like this, is actually this times this, plus this times that, times that. So that generates the first row. The second row obviously is this against these three. So you'll see the AY, AY, and AY, and then the AZ. Now, let's see if this works. It might work, I don't know. So then you start staring in here at these components and you notice something interesting. If you look at a vector I, its length is 1, so I'll do it this way. Dotted with I is nothing more than the length of I, which is 1, times the length of I, which is 1, times the cosine of the angle degree of between them. And in this case, it's 0. So you just get a 1 out of that. So this will give you a 1. But the I and the J are 90 degrees apart. So here's your I and here's your J. So again, the magnitude is both 1 and 1, but now it's 90 degrees, so this is 0. And this is 0. Turns out if you dot any of those, they're all 0. Let's see if I can collect them all. And so the only one you get that's not 0 is kind of this little swipe here, right here. So what you find out is these are all 1, all the others are 0, and you'll get this. Now this is pretty beneficial because now it's also equal to the magnitude of A, magnitude of B, times the cosine of the angle between them. So it's possible if something is left out, or somebody asks you what's the angle between these two vectors, you do this, this, and this, and then you take this A and B and divide it, and you can take the inverse cosine of it, which is what he's doing here. Hang on. But you got to be a little bit careful. But, okay, on the top, this is the dot product, boldface right here, so those are vectors. These are the scalar lengths, and you're going to get something between between 0 and 180. You can also, this is particularly interesting here. I don't know how far down it goes, but say, and I'll give a simple case of that in a second. You can actually find the component of a vector parallel or perpendicular to a line. And at first glance, you may say, why do I want to do that? And I'll show you why in a second. And I think maybe I'll do it now because I'm not sure I like exactly what he's got there. So let me just go and kind of do it here. So if you look at it, give you a kind of a, you know what, do like this and sort of. So let's say you had, did I do something? No. Let's say you had a big tree sitting here with all the limbs that were cut off. Like the guy came and did that. That's one of the things I've learned is when they come trim a tree close to your house, they cut all the limbs off one at a time, and you're left with this big tall thing out there in the middle of the yard. Then they're trying to cut it and make sure it doesn't fall into your house. So the guy actually went up there and took this little special pad rope and cable-like thing and connected to it, and connected to this winch on his truck, and just pulled, Well, this guy's over here with a chainsaw to cut it so it'll go that way. I tensioned the thing, and I think what happened is as the thing started falling, the winch had a tension on it, and it just kept pulling it. But let's just say, and what I'm going to do, I'm going to call that X. I may have kind of pushed this too high up on the page, but it's okay. There's X and there's Y. And I'll say, I'm going to make it simple in that he's 45 degrees there, and he's pulling on this. And say, I have no idea what his thing, say it's 1,000 pounds. I mean, it probably was close to that. So if you break it down, you know, yeah, I'll move the, I don't know where else to move the 45. You know what, I'm going to move this out here, X, so that I can do this. And you know what, maybe I need to shorten that vector so it won't go so far here. So what happens to you is 1,000 pounds divided by square root of 2, and 1,000 pounds divided by square root of 2. Now, what you're saying here is I have a component that's essentially he was pulling the tree kind of down into the ground a certain amount, but also up at the top he was pulling it over to the side. And that was because you knew that was 45 degrees. Whoops. Now, so your case in point is you may want to know this load. And you may not care about, but you may want to know that one too. Just so happens that's 45 degrees. Let's go look at a particular case where, and maybe I can look at his and see if I can find one. He doesn't really have one per se, but let's say you had a vector. Let's say you had I'm going to make it, well, let me just keep that one because in essence, what you could do is say I could have a unit vector. Let's say I'm mostly interested in the pull over here, and that's all I'm interested in. And so let's look at this from the standpoint of, okay, I'm gonna ignore everything and I'm gonna put the 45 degrees back on there in a second. And now I'm gonna take this force and redraw it down on the page, and I'm gonna redraw this in a hopefully, so here's your X, here's your Y. And it just so happens that, of course, here's your I, and then I get this other force here that is, I didn't come up with a name for it, so I'll just call it F. So that force just happens to be 1,000 over square root of 2, that's going to the right, 1,000 over square root of 2, J that's going down. Now, just so happens somebody says, I want to know the force in that direction. Now, this seems stupid, but if you do F dotted with I, what you're doing is you're taking the magnitude of F, the magnitude of I, of the cosine of the angle between them. Wait a minute. Okay. So the first thing that's unique here to this is this. And this is something that he talks about back here. I don't know that he talks about it that much, but he talks about a direction of a line specified by the unit normal, not not unit normal, unit vector. I keep saying that. And since U of A is UA1, we can determine the magnitude of A directly from the dot product. Meaning, let me find it again. Meaning, since this is a special case, because since this vector you're dotting against is length 1, you're going to find out, hang on, where did it go? There you go. I'll just do it like this. That's going to be some number, but if you go in here, this seems weird, but I'm dotting this here. I'll just do it completely. No, that's a minus. Dotted with the I, without that, means the I dot the J gives you nothing. The I dot the I gives you basically 1,000 over screw root of 2. Now, the other way you could look at this is, okay, I've got the magnitude, 1,000, and I could go in here, hang on, is it there? Cosine degree of 45, and if you look at that, 1 divided by square root of 2, they're actually the same thing. So you essentially look at it like, and now I know I basically said A is equal to A, but now let's look at a case where essentially you're looking for dot product and find, so let's do it like this. I and J. So we'll try to draw it somewhat that way. I'll say here is some structure that exists out here, and it's being pulled over to the side with a force that I'm just going to make up, and I'm going to say it looks like it's 100 pounds in the I and minus maybe 60 pounds in the J. So it's this distance is about 100 and that distance is about 60. But then I'm going to say out here to this end of this point, I guess I'll say this is O and this is the A where the thing is coupled to. I want to know what, okay, it is true. I can break that down. But that's no good to me, because what I really want is I want this. What I want to know what's the force pulling it out this direction, and what's the force pulling it down this direction. And so if that makes sense to you, I hope it does. Let's try to see if we can figure this out. Let's assume that this thing has so we have a unit vector, I'll say probably unit vector 1, and then I'll call this one unit vector 2. Or maybe I'll just work on unit vector 1. Let's say that this thing is at the level of a 3, 4, 5 triangle here. So the unit vector 1 that we have right up here, let me think about this. Or do I want to list it as the angle? Yeah, I'll do it this way. Yeah, I'll list this down here. So the unit vector, and so this would be Okay, so of course you have to remember this is a vector of length 1. So if this is length 1, this has got to be 4/5, and this has got to be 3/5. Oops. Sorry, my hand went awry there. So that's 3/5 down there. So what I did, kind of copied that. I couldn't figure out how to put that and that together on the same diagram. So sorry about that. So in fact, if you looked at this, it'd be 4/5 I plus 3/5 J. Okay, so I kind of want to get this part out of the way, so I'm going to do this and move it over here. Now, if I want to know the force component going in this direction, what I have to do is take the force, that force, and dot it with this vector, which is of unit length, and I just put a subscript 1 because I don't know if I'm going to do the 2 or if I'm just, it works the same either way. I may just go to a problem in the book. So if you look at it, first of all, you pretty much can figure it's going to be in that direction. You can tell there's a component pulling it that way. But it turns out you can just multiply 100. So what I'm doing is multiplying this number times that number. And this number times that number. Because that's what we kind of found out a minute or two ago. 4/5. And then it looks like I got a minus. 60. 3/5. Okay. Let's see if I can make my way. Okay. And that becomes what? 44. So it's about 44. Why did I say 45? So it's roughly 44. So that's the component of the force. Sometimes they'll list it FU, and if I've got that, I'll say that. So this is a scalar value, the force in the U1 direction. It's 44 pounds. So the next question might be, hey, now that I see that, well, anyway, let me stop and see if that makes sense. So essentially, you're finding the component in a particular direction. And let me go see if I can find one in the book that looks like this. So that's all he's doing, is he's just picking a particular direction, which he's done something for AA here. And it turns out it's nothing more than looking like a cosine. So in other words, if there's two vectors, and you want to know the length of this in that direction, you just take whatever that is, A, and then you take A cosine theta, and you get that there. Well, if the unit vector here was length 1, it turns out you're doing nothing but a dot product. Now, if you want to see why I believe it should have been done before, I'll show you this. I mean, you've seen it. You've actually seen it. And the reason it should have been done before, in my opinion, is right here. So if you take this vector A, and then you say, hey, I want to know this big long vector, I want to know its length in the x direction. So what do? You take the vector A, you dot it with I, that becomes the magnitude of A, magnitude of I, what did I do there? Times the cosine of the angle between them. What's the cosine of the angle between them? It's alpha. What's this value? It's 1. So suddenly what you see is this term is what's usually called AX. So then you say AX is equal to the magnitude of A times the cosine of alpha. Well, wait a minute. That's exactly what this is. So these were generated by dot products. So they should have introduced you to dot products, got you used to that a little bit. Then they could have gone in here and done that. And then, so, but, you know, they just gave you this formula and said, well, why don't you accept this for now, and we'll deal with it later. And so at this particular point, and the reason I think it should have been done earlier is because dot products are way more powerful than most people give them credit for. They can do a lot of things. And by the way, there's vector dot products, but there's also dot products in, you know, 2-dimensional, 3-dimensional, 4-dimensional, so on and so forth. Okay, I'm trying to figure out. Okay, there I am. Okay. Let me just go pick up a problem that looks fun or interesting, and we'll just do it here. Okay, hang on. All right. This one looks good enough to me. So, let me grab it. Go over to the page. I guess this is probably fun. I'll just go down to here. And I'll dump it in there. Okay, so yeah, up above it, just none of that has anything to do with anything below it. So it says, find the magnitude of the projected component of the force on OAs on this pipe. So what first thing you got to do is you got to figure out what's F vector. Okay, so the F vector, and I'm going to just, it's going to be what's 400. Well, first, I guess I'll go above it and say, I'm going to say a vector R A drawn from A to B is equal to, and with that in mind, I'll go ahead and do the arc. So, how do I transverse here? I go, now it's hard to do this in one swoop, but I think I can. I'll go that distance, then I'll go a distance here, and then this is not working out very well, and then I'll go here we go. Maybe I'll just do it visually. So how far in the X would I need to go? I would need to go 4. Then how far out do I need to go? Well, this I got to look at, because this is 4 meters out. This is 5 meters out. So for me, that means I got to go 1 meter. And then how far down I go? I got to go down 6 meters. 6K. Now let me see if I can do that again. So if I go about 4. Oh, that's right. I can do a select. And then I go somewhere around a 1. So that's about a 1. And then what I'll do, I'll go somewhere about a 6. So I got those. Now I'll grab each one. So I go that far. I go that far. And then I go up there. So looking at it, hey, cool. Okay. Now what do I do? Okay. So in other words, I went a distance of 4. Then I went a distance of 1, and then I did a distance of 6. So I got an RAB. So I want a unit, yeah, that's good enough. Unit vector AB. And you know what? Did I get Oh, I pushed the wrong thing. Whoa. I want to get, first let me get back to here, then I want to get right there. Okay, so I want to do a clear the screen. And now I want to list this as RAB equals to 4, 1, and minus 6. 4, 1, minus 6. Now I'm going to find the unit vector. The unit vector AB is equal to RAB divided by the norm of RAB. Doesn't look very happy there. I wonder what the norm of RAB is. Oh, it's something kind of weird. Okay, so I get 0.54. Yeah, I'm gonna basically. Oh, I know. I'll put this in the window. Okay. So 0.549. 44 I plus 0.13736J, is that right? Minus 0.82416K, that's the unit vector. Now, if I want to know the force, it's 400, the magnitude, times the unit vector. That'll give its direction. So if I want to go back here, now I can say the force is equal to 400 times, what do I call it? UAB. Okay, so I get about 219.77 I plus 0.50, what was it? 54.94J, and then minus 329.66K. Now, does that make sense? Yeah, I guess it sort of makes sense. If you compare these magnitudes compared to each other relative to the lengths of each of these little subvectors. Okay, so here's the thing. This is the largest at a value of 6. So this is the largest distance. This is the second largest distance. And this is the third largest distance. So it makes sense. That's the largest. This is the second largest. And there's your third largest. So they should kind of mimic that, the length kind of similar magnitudes. Like if I got this one to be 90, and this 219, and this 50, I'd know I'd have a problem because this distance is 6, which this distance is not smaller than or larger than that one. So you need to just look back and see if it makes sense. Okay, now the next question is, I want to know the magnitude along the pipe. So what do I need to do? Okay, I can go ahead and take those off. I need to find a unit vector that points, and I'm just going to point it in the direction. I can point it this way or that way, because he says find the magnitude. There really doesn't have to be a direction here. You'll find out if you dot it, you'll get a different sign, but it's the magnitude. So technically I could go this way, could go that way, could go the other way, I don't know. So what I do know is it appears to me, because he put this line vertical and touched the axis, that a vector drawn to here to A would appear to me to go nowhere in the I. It would go 4 in the J, and it would go 6 in the K. If that's the case, and I think it is, Then what you can do is turn around and say, well, I know I have RA equaling to 4J plus 6K. Now I want to turn around and find the unit vector in the direction of A because I'm going to dot it against this force in a minute. Well, that's going to be, the vector A over its own magnitude. So, with that in mind, here, maybe it is better to use it. I don't know. So what I've got is to come up with RA. And that would be 0, 4, and 6. And then I want to find the unit vector A. And that'll be RA divided by the norm of RA. It's going to come up to be kind of a funny number. 0.54. Okay, so 0.54. Nothing cross my elbows here. Oh, no, I don't want to do it that way. Yeah, that's good. Here we go. 5, 7I, 0.83205. Okay. That was the J, and that was the K. There wasn't an I. Now, I have that vector. You can see it sitting right there. There it is. And you can see this one sitting right there. So here's what's cool. You can do it in dots. Since these two vectors are already listed in there, I can do F with, what is it? UA. It gives me a number. I can also do this. And this will show you that it doesn't matter the order. Yeah, okay, yeah. We get the same answer there. Here's what's also interesting. I can do, okay, so I can do, this may seem weird to you, so let's see, you think about it, this is a 3 by 1, so I can do F times UA transpose. You get the same thing. So essentially, this last one is if you listed them as a vector. In other words, if I list them like this, 219, I'm taking this, 219, 54, and minus 329, put it in a matrix where this is the blank, and here's the other one, which is 0.554.832, and you multiply those out, you'll get this number times that, plus this number times that, plus that number times that. And that'll be your dot product. So in essence, what I'm saying is, I take that and dot it with any vector, but in this particular case, I'm dotting it with A, and this time I get a minus 2, and 43. Now, with some change. Now, why is it minus? And that should, you should ask that question. And here's the reason. So I have decided to draw this vector in this direction. And yet you can kind of tell this appears like there's a component going here down in this direction. So in fact, since they're going in the opposite directions, you're going to get a minus sign. To give you a case in point, watch what happens. Okay, if I want this vector, instead of going this way, if I want it to go this way, I just multiply it by minus 1. Meaning, if I went back and went to the original and said, hey, I want the vector to go in the other direction, well, guess what? It's 243. It's in the positive direction. So, so that's kind of the way you do that, is you can use this vector and dot things around all over the place and stuff. So I hope that makes sense. But these problems are one after another. I'm kind of hesitating because I look at the time and I'm like, okay. And I would keep going, except I got to go to the next room here shortly and do another. So all of these look the same. I mean, here's a particular case. I like there's one down here. There used to be one. Yeah, this is a good one. In which, yeah, you're pulling this up, right? But actually, I mean, he may be asking one question about this, but here's another interesting question: is the hinges are sitting down here. They take no load going up and down. In other words, you can open that door. There really shouldn't. The hinge won't. It doesn't hold that door from going up and down, but it does hold that door from sliding this way or that way. So those hinges are catching that load. So in essence, you could dot that. Unfortunately, he's already lined them up with the Y. But in other words, you could say the one I'm interested in is that vector, which happens to be J. So that might be. These are a little bit. Same thing here. Oh, here's a good one. Wait. Well, there's a good one next to it, too. So here you got a bunch of pipes together, and this thing is pulling it. Well, obviously, it's going to be pulling it in such a way that it's probably going to want to twist and do a lot of stuff. It looks like the rope is attached to here. It's going to want to twist and do a lot of things to this. So you might want to know, for example, as you do it, are you interested in, say, if there's too much axial load here? So you might want to know that component in that direction. And he says perpendicular to segment DE. So that's another thing that we need to do, but I guess the time is. You know what? We'll look at this one next time, because there's an extra component here. After you find it along a direction, you got to figure out how to find it along the second direction. Yeah. So I guess I'm sorry I started late, but I got into class and couldn't get the thing going in time. Oh, I didn't do the word of the day. Do we got a minute? Let's do that. Okay, wait a minute. I might be able to get in there real quick. Yeah, I hear you. How about, okay, come on, computer. I need to do that right off, first thing. Oh, come on. Come on, here. And I found a word generator thing. It generates random words for me, so I don't have to bring them up. So let me open my random word generator. And okay, today's word is follow. There you go. There it is. Now I'll sign off.